hole-based system and sound-based, and the shaft-based system basically is the two basic systems basically in this limits and fits measurement. So one is based on hole. So the hole remain unchanged, whereby we change the shaft to fit the hole. Another one is that the shaft remains unchanged, and then we alter or we change the hole to fit the shaft. All right. So the hole-based system basically is that we maintain the size of the hole. All right. So of course with the certain plus minus, okay, and then this manufacturer will actually control the size of the shaft to fit the hole. All right. So another approach is the shaft-based system, whereby this shaft is fixed at a certain range of size, whereby there's still a plus minus there, right? So, but however, we actually manufacture or we alter the size of the hole to fit the size of the shaft. So the other way around. All right. So we are going to go through a series of video. Okay, today we hear some of the experts say about it. All right. So, all right. Enlarge this. Okay. All right. Here we go.
Hole basis system. In this video, we are going to see about hole basis system. The different types of pits are obtained by associating shafts of varying limit dimensions with a single hole whose lower deviation is 0. Consider a basic hole. Clearance shaft. Clearance fit. Basic size. Clearance.
So you can see that if this size here, the basic size, just now you see the two green line, right? So in the ideal case, both also having the same basic size. But however, that we know that this basic size actually cannot be achieved. All right, like for example, diameter of 50. Okay, so in an ideal mating of this hole and shaft, basically is 50 mate with 50. All right, and that will be the most perfect fit. But however, due to this limitation that we have in the manufacturing, so the 50 and 50 mating is basically impossible. So there will be a plus minus. All right, there will be a plus minus, so that in the end, we do not want it to be too randomly being made. All right, too randomly being made means that we cannot actually control it to meet our requirement, because in the end, what will produce will be the clearance, interference, and the transition fit. Okay, so sometimes for some of the application, we need it to be clearance only. So we can't let this hole and shaft basically having the numbers being randomly created. So we fix one of it, and then we strictly control the other one, so that to make sure that it is always clearance, it is always interference, or it is always transition. All right.
Zero line, tolerance zone of hole, tolerance zone of shaft. When the lower deviation of the hole is 0, the minimum limit of the hole will be equal to its basic size, which is taken as the base for computing all the other limit dimensions. The limit dimensions on the hole and the shaft are computed by selecting suitable clearances and tolerances on the shaft and the hole. Interference fit, basic size, interference fit. Basic size, 0 line. Interference or negative clearance. Tolerance zone of.
So as you see that just now, the comparison of these two, the clearance fit, whereby when the shaft goes into the hole, always there's still gap. You feel loose. All right. for this is interference means that if you can see from here, all right, this shaft is generally always bigger than the hole. All right, so that when it mentioned that more power is required, more energy is required, sometimes you have to even heat up the hole to expand it and then only insert the shaft, and then when it cold, then it will grip tightly to this shaft. So that's how sometimes the bush, the bearings, and so on is being installed or being assembled to this shaft, and so on.
Of shaft. Tolerance zone of hole. Force is required to insert the shaft. Shaft basis system. In this video, we are going to see about shaft basis system. In this system, the different types of fits are obtained by associating holes of varying limit dimensions with a single shaft whose upper deviation is 0. Consider a clearance hole. Basic shaft, clearance fit, basic size, clearance, 0 line, tolerance zone of hole, tolerance zone of shaft. When the upper deviation of the shaft is 0, the maximum limit of the shaft will be equal to its basic size, which is taken as the base.
Okay, you do mention there is a phrase, you do notice that there is a phrase here. It says the upper deviation is 0. Means that in shaft-based system, all right, if it says that the diameter is 50, means that the upper maximum value for the shaft is 50 only. It's up to 50.0. But the plus minus, it should be something negative. Means that it can be smaller than 50, but it will be no more bigger than 50. All right. So for the hole based system, the minimum deviation is 0. It is mentioned in the video just now that no matter how small it can go, okay, how big it can go, it will no longer, it will never be smaller than, let's say, 50. Means if the diameter is 50, the minimum size you can get is 50. So that's why one of these example that we can see in our notes is the 50 H7. The H7 is what figure? 25, 0. The bottom will always be 0. And for the shaft-based system, the top will be 0. Okay, 0, 25, something like that. And for the hole-based system will be 25, 0. Means the smallest hole size will always be 25 or 50, and so on. It will not be plus minus 0.4, something like that. It will be from let's say a certain range. So the minimum size will always be the basic size for hole-based system, and the minimum size the maximum size will be always, let's say this basic size for the shaft-based system. All right, so we'll come back to this later on.
For computing all other limit dimensions. The limit dimensions on the hole and the shaft are computed by selecting suitable clearances and tolerances on the shaft and the hole. Interference fit, interference hole, basic shaft, force is required to insert the shaft, basic size, 0 line, interference or negative clearance, tolerance zone of shaft, tolerance zone of hole.
事实上呢，股票投资就像建一栋楼，对一座建筑物或一栋楼来说呢，最重要的不是它的
Welcome to my YouTube channel Modi Mechanical Engineering Tutorials. Today I am going to explain a basic concept of mechanical measurement and metrology, and that will be hole basis and shaft basis systems. Now for this, two systems of hole basis and shaft basis of the fits for obtaining clearance, interference and transitions, when that will be the assembly of the two components. So let us see first one, and that will be the hole basis systems. So as from the hole basis system, just you can refer the diagram. So that will be the zero reference line, and for hole basis systems, just you can see the hole tolerance, or you can say hole size, that will be assumed with the zero lower deviations as the basic size. So hole basis system with the lower deviation size with the zero line. And just you can change the dimension of the shaft tolerance for making an assembly of the two components. So basically, so the hole size is kept constant and the shaft diameter is varied to give the various kind of fits. So let us see onto the diagram. So that will be the first hole tolerance and shaft tolerance. So if that will be some clearance between these two, so that will be making some difference, or you can say gap. So that will be making a clearance kind of fits for the different positioning of the hole tolerance and shaft tolerance. If according to the hole basis systems, what it says, the hole size is kept constant. So that will be the similar over here, and just shaft diameter is varied to give the various types of fit. So just you can change the positioning of the shaft dimensions. So if it will be like this, or you can say into the hole tolerance, or you can say some kind of, so that will be nothing but some kind, it will be act as a clearance fit, or sometime it will be act as a interference fit. So that will be the intermediate zone, or you can say the transition fit. Now for the third case, according to the definition, the hole size is kept constant. Just you can see that will be into the same position. So you can say that that will be the hole tolerance. And that the upper side, that will be the shaft tolerance. So hole tolerance, it will be into the lower side, and shaft tolerance, that will be the upper side. So it will be making a always one kind of interference zone. So that will be called as an interference fit. So just you can refer, the hole size is kept constant. So for all the three cases of the clearance fit, transition fit or interference fit, the position of hole tolerance which will be same, or you can say kept constant, and just you can change the diameter is varied of the shaft, and you can get the different kind of fits. So that will be the clearance, transition and interference fit. Then in the case of the hole basis systems, the lower deviation of the hole is becoming zero, we already discussed. The upper limit of the hole and the lower limit of the shaft are then varied to give the.
So you can see here in this system, the lower deviation at the hole is 0. You can see that you draw a line here. Let's say if this is diameter 50, so this particular line here, the 0 line is 50. All right, so it will be no lesser than 50. Means that the lower deviation, the minimum hole size will always be, let's say, 50. It will not be 49.9. Okay, so it will be anything more than 50 up to, a certain grading of this hole. Let's say, like for example, in our example in the notes, 50H7, it will be plus 25 and 0 at the bottom. You always see 0 at the bottom. Okay, so if for this shaft, the shaft size will be always 0 on the top. If it is a shaft-based system, it will be 0 on the top, but numbers at the bottom. So the maximum hole shaft size will be as the basic size, which is the diameter, let's say 50, it will remain maximum 50. Okay, and it can be it will be always lesser than 50 or 50. All right, if that's the shaft-based system, we need to control that strictly to know that maximum the size will be 50 only. okay? Or if it's in a hole-based system, the minimum of the hole will always be 50. Okay, we'll make the hole 50 or bigger. In the shaft-based system, we'll make the shaft anything that is 50 or slightly below. Okay.
The desired types of fit. So basically, clearance.
So if in the questions, in the test or anything, if they never tell you what is the if you know that, or if the question is asking about this hole-based system, it will tell you that the smaller size is let's say 49.8, but it never mentioned about the maximum size. It will be automatically 50. All right, it will be automatically the minimum size. Sorry, if the minimum size, they never mention about the minimum size, but they're telling you that this diameter is having the maximum size of 50.2025. So in the end, we will know that this thing is automatically the basic size is 50. Okay, the minimum, okay, hole size is 50 to the maximum 50.0.25. Okay, in as mentioned in the question. So it will be by default. Okay, so similarly for the shaft, means if they never tell you the maximum shaft size, okay, if it's a shaft-based system, but they blah 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 about the minimum shaft size, you know, and so on, you know that the basic size is the diameter of the maximum value also is the diameter of this, so it's similar to the basic size. All right.
Transition and interference kind of fits for the hole basis system. Now I would like to explain a shaft basis systems. So in case of the shaft basis system, the shaft size is kept constant. So now just you can refer the figure. This one is the size of the shaft, or you can say shaft tolerance, and that will be kept constant. For all the three cases of the clearance, transitions and interference, it will be kept constant. Now just you can change the dimensions of the hole tolerance. So just you can refer the figure number 1. So that will be the shaft tolerance. So in that case of the shaft tolerance, the shaft size is assumed with the 0 upper deviations as the basis size. So that upper part, that will be touched with the 0 reference line, and that will be the hole tolerance. If you can find any gap between these two, like this, so that will be making a clearance, so that will be called as a clearance fit. If you can find, or you can say you can change the hole tolerance according to this figure, so that will be the intermediate zone of the clearance and the interference, so you can say that that will be the transition fit. And for the third category, so that will.
So this particular figure basically tells you if the shaft tolerance, okay, if the shaft tolerance always smaller, so if this is the line here, so if the shaft, so the hole is up here, okay, the shaft is up here, so this indicate that, so you can see from here, this indicate that, okay, that the hole is always bigger than the shaft. So whenever you insert the shaft into the hole, it will be always loose. So this indicate that, okay, you can see that the hole size, you know, is at 3 stages, sometimes bigger. Okay, sometimes the hole is bigger than the shaft, sometimes it's in the between, sometimes it's loose. So it means that this is a transition fit, you know, sometimes fit, sometimes loose, sometimes tight, sometimes loose. All right. So this one, okay, whereby you see that the shaft is above the hole system. The hole tolerance means that it's always a tight mating or the tight assembly.
Will be the shaft tolerance we already described like this, that will be kept constant. Just change the hole. So if you find the hole tolerance, the below of the shaft tolerance, so that will be always making an interference fit. So in case of the shaft basis systems, what you remember, the shaft size is kept constant. Just you can change the dimensions of the hole tolerance, and you can get the different kind of positionings of the shaft and the hole, and you will get the different kind of fits like a clearance fit, transition fit, and interference fit. So if you like this, then subscribe and share Modi Mechanical Engineering tutorials. Thank you very much.
You can make a professional, engaging video with no camera and no editing, even if you've never made a video before in your life.
Welcome to my YouTube channel, Modi Mechanical Engineering Tutorials. So in this video, I would like to differentiate the hole basis systems and shaft basis systems. So for the detailed study, you should refer my previous lecture for the study on the hole basis systems and shaft basis systems. So in this video, I am only the differentiate between hole basis and shaft basis systems. Now for hole basis systems, yes, you can see the first difference, the hole size is assumed with the zero lower deviations, or you can say H hole as the basic size. So just you can refer, so that will be considering as a zero line. So in case of the hole basis systems, the hole size is assumed with the zero lower deviations. So just you can see the lower part that will be onto the zero line. So that will be the hole systems. And the different kind of positioning of the shaft. So suppose that will be the position of the shaft. So that will be initially the hole size is assumed with the zero lower deviations. So that will be the lower deviations with the zero line. So that will be called as a hole basis systems. Now for the shaft basis system, the shaft size is assumed with the zero upper deviations, or you can say small h shaft as the basic size. So what happened for the shaft basis systems? So here that will be shaft basis systems. So that will be the upper deviation, that upper part. And if that will be the positioning of the hole basis system, or you can say hole. So that will be the two different positioning for the hole basis and shaft basis. So here that will be the hole size is assumed with the zero lower deviations and shaft size is assumed with the zero upper deviations. Now second one, in order to obtain the desired types of fits, limits onto the hole and kept constant, and sum of the shaft R is being varied. Now first one, that will be the initial position of the hole and the shaft. So if you find any kind of gap between hole basis and shaft basis, so you can say in technical language that will be providing the clearance for hole system and shaft system. So that will be making a clearance fit. But in case of hole basis systems, the hole that will be kept constant. So that will be the hole, and these are the different positioning of the shaft. So if it will be the clearance fit, or either you can say the some kind of interference fit.
Okay, I'll make another approach of explanation on this to make you clear about it. So I'll stop this sharing and then I'll go to free sketches mode so that I can sketch. All right. So what it means here is that let's say if I have this, okay, let's say if I have a line here. Okay, this say that this is diameter 50. Okay, so still remember one of these example in our class in one of our class. So it says that the hole size is having the diameter 50 H7, and then the shaft size is having a diameter 50 N6. So if you refer to this, still remember the process of how to find the H7 and N6 by referring to the table. So let's say this is a hole base system. So we refer to the hole basis system. So we only need to find out that this is diameter 50 plus 25, 0. Okay, so and then this the shaft size is the 50, 33, 17. If I'm not mistaken, it's both plus. Okay, so the meaning is like this. Okay, so it's telling you information that the basic line here, the basic line or the zero line, so it's telling you that this mating is a mating of 50 shaft and the 50 hole. All right, so it means here that this thing is at plus 25, 0. Okay, so and the shaft is something like 33, 17. So 33, so I use another different color to basically show it. So let's say 17 is somewhere here. So this is plus 33 plus 17. So if you can see that when this shaft at this size plus 17 entering here, okay, means that it is still loose. And the minimum size forever will be 25, will be 0. Okay, so if this plus 17 is going to go into plus 25, so it will have a gap here. So this gap will always ensure that, or this particular gap here basically tells you that this thing is loose. You have a smaller shaft entering a bigger hole. All right. So if I enlarge this, okay, if this is 33, however, so when we look at this, so there is a gap here. So it's telling you that this thing is the shaft, basically, this shaft is bigger than this hole. So this is tight, and this is another one here is loose here. So it will be between tight and loose. So this will make this particular assembly will become a transition fit. So similarly, if you see something else, okay. Let me rub this off. Oh. Okay, similarly, if you see some other cases, for example, like if I have this, okay, so let's say if I have this, okay, so still let's say this is 25 and 0 plus, okay, so if I have something that is, let's say, 33, 50, so if you can see here, if you see it here, okay, it's always bigger. Even if this, let's say this shaft, okay, is always bigger than the hole. Okay, even if the 33 is bigger than 25, even if 50 is even more bigger than 25. So no matter how you look at it, there's still either the small gap or a bigger gap. So you know that if I want to actually install or make or assembly this shaft into this particular hole, it will be a tight assembly. Means that it will be an interference forever. Okay, so in this particular video, it shows you that they actually put this thing together. Okay, they actually put this thing together in one is dark color, another one is red color, I think, so that to see how this thing actually overlapping each other. Okay, so actually if I want to shift it, I want to put it aside so to make you see the clearer picture. Okay, so that you can see clearer that the shaft is always on a higher level than or on the lower level or at the same level. That would determine the whether it's a clearance, whether it's an interference, whether it's a transition. All right. Okay, I'll stop sharing for this one, and then we go back to the video. All right.
But if you find the intermediate, so that will be called as a transition fit. But so once again, the hole that will be kept constant, and if you find the shaft, that will be the upper side of the hole. So that will be the shaft, and that will
This is the one that I mentioned just now. The shaft is the shaft is always bigger than the hole because it's on top, or either if it's bottom, okay, means the shaft is always smaller. If it's intermediary, means some on top, some in the middle, just like this middle figure here. So this is a transition. Sometimes bigger, sometimes smaller, sometimes loose, sometimes tight. So for this one, the shaft, the third one, okay, the currently he drawn this one. So this one is always tight, okay, because it's always the size, no matter how you look at it, the minimum shaft size and the maximum shaft size also will be bigger than the hole.
be the hole. So what happens? So you can find the such kind of alignment of A and B components for the assembly. So that will be called as a interference fit. So basically transition fit, that will be the products of either that will be as a clearance fit or that will be for the interference fit. But these three kind of fits only changing with your shaft dimensions. As you can see, the whole positions that will be kept constant. So just you can change with the shaft. Now for the shaft basis systems, in order to obtain the desired types of fits, limits onto the shaft are kept constants, and same onto the variation with the hole systems. So just you can see, for these positions that will be the shaft and that will be the hole. Why that will be the shafts? Because the shaft size is always assumed with the zero upper deviations. So that will be the shaft and hole. Now for the second one, the shaft are kept constant. So that will be the same. You can see that will be the shaft. And if you find the different kind of positioning of the holes similar to the transition fits like this.
Okay.
So that will be the hole. So if you find such kind of arrangement, so that will be called as a transition.
So I back in this drawing again, okay, back in this page again. So particularly this is telling about the shaft-based system, whereby we have this zero line here or the basic size line. Okay, so we will be telling you that, okay, there what he's been telling is that, okay, the shaft, okay, being produced, let's say here, okay, so let's say the shaft, okay, we put it as a shaft, okay, okay, the size, let's say this is the diameter 50, okay, so the size here, so this line is at 50, so it will be forever, the maximum size is 50, so it can only be smaller, not bigger. Okay, it will be 50.0. The maximum value will be 50.0. This is shaft basis system. Okay, shaft basis system. We fix the size of the shaft, and then however the variation is on the this hole. Okay, so whenever, let's say if you are to produce anything that is bigger, okay, so like what it shows you, it shows you on top, so this is hole, this is shaft. So if it is, the size is always, you know, on top of this shaft, means that there will be no problem inserting the shaft into the hole. You always get a loose assembly. All right. So the most troublesome one is always, you know, in the middle section. You know. So let's say, okay, let's come back here. Let's say let's say we put aside here, we put beside here rather than on top of this shaft. Let's say the size of the hole is something like that. Okay, it's well above this line, so it means that sometimes it will be bigger than the shaft, and also it is well below this line, so it means that it will be sometimes smaller. So that's what you see, you know, he draws here, 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 you know, he draw the three square here to indicate that sometimes it's just right, sometimes it's smaller, sometimes it's bigger. So actually, if you put into the drawing, it means, okay, hole, shaft. It means something like this. It's always the hole size is bigger than the shaft. The variation, the range of it, when it becomes small, when it becomes the minimum hole size, you know, it will always like this. When it become maximum, it's bigger. When the minimum is tight, you know. So there's kind of sometimes tight, sometimes loose, kind of mixture in terms of assembly will appear or will be resulted. Okay, so is this what you want? Maybe. Okay, maybe for some application, yes. Okay, but it gives you an idea. Okay, so that we can actually control it. All right.
Position, fit. And for the third one, once again, the shaft, it will be kept constant. And if you find the hole, that will be the below of the shaft, so that will be always making a interference fit. So these are the basic difference of the hole basis and shaft basis systems. Now for details, to control the hole basis and shaft basis systems, so for the hole basis systems, it is more convenient to vary the shaft size to get the required fits. So that will be the convenient method for assembles of the hole basis systems and shaft basis systems. We can easily adjust it. But for the shaft basis systems, that will be having the difficulties to vary the hole sizes to get the required fit. Some more difference for hole basis systems, it is cheaper and convenient to make the hole of the correct size Thus, these systems is preferred into the mass productions. So whenever that will be the requirement of the mass productions in the field of the any measurement or any kind of productions, so that will be the having the good feasibilities. But for
So like I mentioned previously that the whole base system actually is more preferred, all right, because it's easier to make a hole than making a shaft, okay, because of these cutters that involve, and so on, the process that is used to produce the hole and the process that is used to produce a shaft, the shaft is a long thing, all right, so the variation might change on this length of the shaft, first of all. Okay, the size that you measure. Let's put it in another sharing mode. The sharing page. Okay, let me rub this off first. Okay, so let's say if you will to produce a shaft, okay, the size here, the size here, the size here, and all along this thing, it might change, it might varies. Okay, so yeah, if you measure this and do the assembly so that this one fit into the hole, initially it might be fine. Okay, and then maybe all along the way you might feel that sometimes it will be a little bit slightly tiny bit of tightness, and not or feel like not as loose, something like that. You will feel like it. Hey, how come it become tighter all the way? Yes, it should be this way. Because why? Okay, because in these productions of this shaft, normally we will have this thing. Also later you will learn. So in the lathe machine, so we will put this thing clamp. Okay, whereby you have this cutting tool, basically to reduce the size, okay, to smoothen the size or to achieve a certain size. But however, ideally, yes, you should be achieving a similar size all the way. But however, we do not forget that this thing wear and tear, especially the cutting tool. All right. So when it become wear and tear, so maybe the initial surface is initial cutting tool is something like this, very sharp. Then later on, okay, this cutting tool might become blunt, something like that. Okay, so it become blunt. So you need to actually resharpen it. Okay, you need to actually resharpen it, recondition it. Okay, all the time. So this thing is very difficult and very subjective. First of all, we do not know when it will become blunt. We do not know when the wear and tear will happen. Okay, and also based on the skill of each and every machinist that actually working on it. Some very hard working, they check always, and so on. But however, there's a downside of it. That makes the production slow, because every actually now and then, you have to produce so many shafts, and so on. So if you alone is having the slowest one, other people is producing 10, you only produce 3. Yes, I know yours is very precise, very very nice in size, and so on, no? But still, your productivity will be very low. Okay, so is this what the company want? Maybe yes or maybe no. Okay, that would depend. All right. So in the end, okay, so it's very difficult to do so. Comparingly, if you are making just a hole, okay, so have you ever done something like tabletop drilling before? Okay, so this tabletop drilling normally is like you have this holder, you hold a drill bit, and then you have this workpiece here, and then you have this handle here, you know, whereby you hold on this knob, and then you move this downwards, and then this thing will move downwards, and then you come here, and then you will start drilling, you know, and you can see the chips coming out, you know, and in the end you will form a hole. So if you can see from this kind of cutting tool, normally, okay, this kind of cutting tool is a multi-edge. So you can see that the lines here, okay, there are lines here. So basically, these lines will actually do the cutting. All right, so I'll show you this drill bit. Okay, okay, let's say if we go to here. So you can see that this kind actually is a multi-edge. All right, the chances for it to fail or wear at the same time is actually lesser in chance. Okay, so it might be all right, it might be actually wear and tear might happen in some of the edges, but not all of the edges at one time, for example. Okay, if comparingly if comparingly, okay, I'll move to a certain. If comparingly, let's say for this kind, you know, you can see that there's a one sharp angle here. So it heavily depends on, let's say, I wonder if you can see my cursor, okay? So it's just heavily depends on the sharp edges on the edge. So once this is blunt, means it will affect your whole size of this shaft. All right. So that's why it means that it's easier to produce, or should I say, in another words, it's much easier to control the size of the hole, the limits, the tolerance of the hole, if compared to the limits or the tolerance of a shaft. All right. So this one, just bear in mind. All right, so we go back here. Okay, I need to change another mode. So not share a tab. Okay, go back to this.
The shaft basis systems, that will be the costlier and the time consuming, that will be the main issue to make a shaft of a correct size. Thus, this systems is not suitable for the mass productions. Then for the hole basis systems, for the production, shafts are different size and requires less capital and the storage space for the tools required. And other side, for the shaft basis systems, for producing the holes of the different sizes requires more capital as well as the storage space for the large number of the tools requires. And the last ones, for the hole basis systems, gauging of the shaft can be carried out by adjustable gap gauges, which is easier and convenient. So that will be issues regarding to the measurement of the hole basis systems. And for the shaft basis system, the gauging of the hole is difficult since it is a internal dimensions. So that will be all regarding to the basic difference between hole basis systems and shaft basis systems. So if you like this, then subscribe and share Modi Mechanical.
Hello friends, today we will learn system of limits and fits. Limits we have studied and fits we will see now. Observe diameter of hole and diameter of shaft. Case 1, this is hole and this is shaft. Now observe the changes in case 2. Again, observe in case 3. As we observe, shaft and hole relation in case 1 is very loose, in case 2 it is loose, and in case 3 it is tight. Requirement of looseness or tightness of assembly changes according to the function of assembled mating components. And fit is the degree of looseness or tightness between two mating parts to perform a definite function. Now, fit is classified in 3 categories. Number 1, clearance fit. Second one is transition fit. And third one is interference fit. On screen, you are watching example of clearance fit, where tolerance zone of hole and tolerance zone of shaft is shown with respect to the zero line. In clearance fit, upper limit of shaft must be less than the lower limit of hole. This is upper limit of shaft, lower limit of shaft, and tolerance zone of shaft. Similarly, upper limit of hole, lower limit of hole, and tolerance zone of hole. You can see every time we need not to draw the complete diagram of hole and shaft. Just drawing the tolerance zone of hole and tolerance zone of shaft with respect to the zero line is enough, like this. This is example of interference fit. In interference fit, upper limit of hole must be less than the lower limit of shaft. This is upper limit of shaft, lower limit of shaft, and tolerance zone of shaft. Similarly, upper limit of hole, lower limit of hole, and tolerance zone of hole. Now, here upper limit of hole is less than the lower limit of shaft. And in interference fit, tolerance zone of hole will always be on lower side of the tolerance zone of shaft. You can see here. This is example of transition fit. In transition fit, limits of hole and limits of shaft are arranged in such a way that you may get interference fit or may get clearance fit. This is upper limit of shaft, lower limit of shaft, and tolerance zone of shaft. Similarly, upper limit of hole, lower limit of hole, and tolerance zone of hole. Now you can see tolerance zone of hole is overlapping the tolerance zone of shaft. Now, in this example, the tolerance zone of hole is partially overlapping, but it may overlap completely or partially. Overlapping ensures the possibility of clearance fit and interference fit both. Now we will see clearance fit, transition fit, and interference fit together. This is zero line and tolerance zone of shaft. In interference fit, tolerance zone of hole will always lie below the tolerance zone of shaft. In clearance fit, tolerance zone of hole will always be above the tolerance zone of shaft. But in transition fit, tolerance zone of hole and tolerance zone of shaft will overlap. It may overlap partially or completely. If you observe, hole tolerance zone changing its position to get required fit. But shaft tolerance zone is not changing its position with respect to the zero line. It is shaft basis system of limits and fits. This is zero line and shaft tolerance zone. In clearance fit, upper limit of shaft must be less than the lower limit of hole. It means hole tolerance zone must lie above shaft tolerance zone like this. Transition fit. In transition fit, there is possibility of both clearance fit and interference fit. For that, the hole tolerance zone must overlap the shaft tolerance zone. Then overlapping may be partially or completely like this. Interference fit. In interference fit, upper limit of hole must be less than the lower limit of shaft. Hence, hole tolerance zone will lie below the shaft tolerance zone like this. Now, if you observe, the shaft tolerance zone is constant, but hole tolerance zone is varying in order to get the required fit. This is known as the shaft basis system of limits and fits. Now, shaft tolerance zone position is constant with respect to the zero line. Here, the upper deviation is 0, which is chosen as fundamental deviation. And fundamental deviation of shaft matching zero line is denoted by H. In shaft basis system of limits and fits, fundamental deviation of shaft always will be H, small h. Till now, we have studied clearance fit, transition fit, and interference fit, where shaft tolerance zone position was fixed with respect to the zero line. Now observe the changes. This is hole tolerance zone and zero line. For interference fit, upper limit of hole must be less than the lower limit of shaft. That means the shaft tolerance zone must lie above the hole tolerance zone. Here it is. In transition fit, hole tolerance zone and shaft tolerance zone must overlap to ensure the possibilities of both clearance fit and interference fit as shown in figure. And in clearance fit, lower limit of hole must be greater than the upper limit of shaft. That means shaft tolerance zone must lie below the hole tolerance zone like this. Now, if you have observed shaft tolerance zone changing its position to get required fit, but hole tolerance zone is not moving its position with respect to the zero line. It is hole basis system of limits and fits. Now we will study clearance fit, transition fit, and interference fit together in hole basis system. This is zero line and hole tolerance zone. In clearance fit, as we have studied, lower limit of hole must be greater than the upper limit of shaft. That means the shaft tolerance zone must be below hole tolerance zone like this. In transition fit, the shaft tolerance zone must overlap hole tolerance zone partially or completely to ensure the possibility of both clearance fit and interference fit like this. And in interference fit, the lower limit of shaft must be greater than the upper limit of hole. That means the shaft tolerance zone must be above the hole tolerance zone like this. Now, if you have observed, hole tolerance zone position is constant with respect to the zero line. Now note that the lower deviation is 0, which is chosen as fundamental deviation. Fundamental deviation of hole matching zero line is denoted by capital H. In hole basis system of limits and fits, fundamental deviation of hole always will be H, capital H. And note that hole fundamental deviations always will be denoted by capital letters. Now, to avoid confusion, we will see clearance fit simultaneously in shaft basis system and hole basis system. This is zero line and and this is sharp tolerance zone, whose upper limit is matching the zero line and chosen as fundamental deviation, small h. And this is hole tolerance zone, whose lower limit is matching the zero line and chosen as fundamental deviation, capital H. In sharp basis system, you can see the hole tolerance zone is varying in order to get the required fit, that is clearance fit. And in hole basis system, this sharp tolerance zone is varying in order to get the clearance fit. Now in both the cases, you can see the condition is same. The upper limit of shaft must be less than the lower limit of hole, which is being justified in both the system. As we have studied, in transition fit, hole tolerance zone and shaft tolerance zone must be overlapped partially or completely.
Actually, this diagram basically is very good. As you can see from here, the white line basically show the zero line, and for the sharp base system, it is maximum only at the zero line. Means that if it's a diameter 50, it will be 50.0, and it can be anything smaller than 50. That will be the limits and fits for the shaft. So for the hole base system, the white line here, which is the zero line, so the shaft size will be anytime bigger than 50, above 50. So it can be anything from 50 or more, not less. Okay, for the hole. So for the size, anything from 50 or lesser, not more than 50.
In sharp basis system, in order to get the transition fit, hole tolerance zone is varying its position with respect to the zero line, and shaft tolerance zone position is fixed. Similarly, in hole basis system, hole tolerance zone position is fixed, and in order to get the transition fit, shaft tolerance zone position is moving like this. In the same way, in case of interference fit, in sharp basis system, the shaft tolerance zone position with respect to the zero line will be fixed, and only hole tolerance zone will be moved in order to get the interference fit. And in hole basis system, the hole tolerance zone position with respect to the zero line will be fixed, and only shaft tolerance zone position will be moved in order to get the interference fit. So friends, we have studied all these topics. If you like this video, don't forget to hit like and subscribe button. Thank you.
Have you seen this new flipbook creator? You can create flipbooks and ebooks in just 2 minutes direct from your...
I've wanted to make this video for a while. It's on something I've found very useful over the years, and I hope you will too. The ISO system of limits and fits. Contrary to most of the other videos on the topic,
This is the cutting tool that I mentioned about. You see that the sharp edges here is used to cut. So this is a single cutting. Okay, so it's a 1-point cutting, or there's another one. It's called multi-point. Okay, so the chances for the multi-point to fail actually is lesser, or you need to have a lot of failure or a lot of wear and tear in the multi-point cutting operation. Okay, to actually affect on the size of, let's say, the hole. Okay, if a single point, if once it's being cracked, and blunt, wear and tear happen, actually it will affect all of the subsequent cutting operations, and so on. Right, so we'll learn more about this in this machining process, which is the last chapter of this semester.
I'll be presenting this with a working microphone. If you've seen as many videos online as I have about this, you'll get that joke. Before I get too far into this, I want to say that this is my understanding of the ISO limits and fit system, and I did do my due diligence to make sure it was correct, but if I make a mistake, please let me know in the comments so I can either add edits to the description, or if I'm way off base, remake the video. So starting off, Any dimension in existence has some tolerance to it. The tolerance specifies how much higher or lower a dimension can be from nominal and still be acceptable. The space between the upper and lower limit is often called the tolerance zone.
So this is what I mean here. So if you start from, let's say, the initial of this cutting with this single point cutting tool. So when initially it should be all right. Initially it will still be okay in cutting all along the way. But when it's subsequently, when you are cutting along this shaft, so what if cracks happen, let's say at this point? So the subsequent cutting or this material removal process might not be as according to the
Think about it like
design
football
size.
uprights. Each upright represents a limit, upper or lower. To score a field goal, we kick the ball towards the center. But no matter how the ball flies, as long as it ends up between the uprights, it's acceptable, and our parents will still love us. Before we get any further, I should mention that I'll be talking about shafts and pins fitting in holes. But per ISO 286, this system can be used for internal and external features of size. You'll sometimes see it used for keys fitting in keyways, for example. How things fit together is determined by how much free space there is between the two parts. If there's lots, there will be lots of space for the parts to move. If there's only a little, there'll be a lot less space. Finally, if there's no space, the part won't be able to move. In this video, I'll show the hole tolerance zone is red, and the shaft tolerance zone is green. This means that, without measuring, the actual outer diameter of the shaft will end up somewhere in the green zone, and the actual diameter of the hole will end up somewhere in the red zone. A pin can fit into a hole one of three different ways: clearance, transition, and interference. A clearance fit means that there will always be space between the two parts, no matter how the tolerances turn out. Transition fit means there's sometimes space between the parts and sometimes there isn't, but it's usually pretty close. Interference fits never have space between the parts, and one part always has to be forced into the other. It turns out these categories can actually be quite broad. For example, a 9mm pin fitting into a 10mm hole is a clearance fit, but it would be extremely loose. A 9.98mm pin in a 10mm hole is also a clearance fit, but it's much tighter. The former might be good just to make sure two parts don't hit each other, and the latter might be good for making sure the pin stays approximately in the same position relative to the hole. Different fits, as well as their descriptions, can be found by looking up preferred fits and tolerances in the Machiner's Handbook. There's a preferred fit for most situations, and this is a really good starting point. Also, check out the YouTube video by Tarka on the ANSI system of fits and tolerances. The designations are different, but the concepts and considerations are the same. So if we want a dowel pin to fit loosely in a hole, we measure it, we ream the hole to have a little extra space.
Yeah, this is the one that I mentioned. You see that here? The cutting tool, cutting edge, so there will be multi-cutting edge. Okay? For all of them to fail at one time, or together, or simultaneously, it's very, very difficult. Because unless you are doing a lot of this rough cut, and so on, so you are damaging the cutting tool, then it's possible. But however, normally it won't happen so, right? So you can see that there's a multi-cutting tool compared with the shaft making cutting tool, which is one sharp edges. Just like writing with your mechanic, the 2B pencil, right? So after writing for a while, okay, so this you need to sharpen it. You need to resharpen it to maintain your neat and tidy, okay, and fine writing, because the carbon will slowly blunt, right?
It, and we put it in. The problem arises when you have a bag of 100 dowel pins and you have to ream 100 holes. Dowel pins have a tolerance on them, and their sizes will always vary a bit. Your reamer will also cut slightly different sized holes, depending on your work holding, wear in the reamer, and the cutting parameters, all of which can change while reaming your 100 holes. Because you bought the dowel pins and have no control over their tolerance, this is called a shaft basis fit. So the challenge is now to decide what size reamer to use to make sure that all the dowel pins fit properly. If you know the tolerance range you can expect from your reamer, and you know the tolerances of the dowel pins, you can choose a reamer size where the smallest hole the reamer can cut still has space for the largest dowel pin. This is called the allowance, and is typically something you choose. You're allowing, say, 25 microns of space between the largest dowel pin and the smallest reamed hole. Because there will be other smaller pins, and your reamer will sometimes cut larger holes, you may also find yourself cutting the largest possible hole for the smallest possible pin. The extra space on top of the allowance is called the clearance. If the clearance is too large, the fit might not work. The only way to change the clearance without changing the allowance is to tighten up your tolerance zones, either by changing your manufacturing methods or buying tighter tolerance pins. Conveying tolerance zones can be a bit annoying. Say you own a factory that makes dowel pins. You want to be able to tell customers what the tolerance zone is on each size of dowel pin.
So just a little bit on the information, whereby you can see that this is something like this theta rate thing actually falling down. So this is not the theta rate, yeah. So this is the cutting fluid. So cutting fluid, basically the function of it is to cool down this the heating zone. Means that the contact phase means that the cutting tool when in contact with another metal or anything when during performance of cutting, so it will heat up due to friction, okay, due to the cutting, due to the friction, so it will pile up heats. So as you know that heat is generally a cancer for any metal, so it will actually damage it, okay, change the properties, make it weaken, okay, make it expand, and so on and so forth. So we do not want them to happen. So we provide or we supply it with cutting fluid to cool it down so that it will not be maintained at such a high heat all the time. Okay, so at least we bring down the temperature so that the effect of heating can be minimal. All right.
Is on each size of dowel pin, but it would be cumbersome to have to create engineering drawings for each size. So instead, you can just say the tolerance will always be a bit over the specified dimension, where a bit over scales roughly proportionally to the target size. We could say that all the pins will be between 0.1 and 0.3% larger than the nominal dimension. The problem is we don't want people to have to constantly calculate what these percentages are. The system we use instead is called the ISO 286-2 standard. ISO 286-2 uses numbers and letters to convey tolerance zones, things like M6 and H7. The number, also known as the International Tolerance Grade, roughly indicates how large the tolerance zone is, and the letter indicates roughly where it is. The letter H always means that the specified tolerance zone includes the nominal size as one of the limits, and it diverges into the material. For holes, H means the smallest the hole can be is the nominal size, but it's allowed to be larger. For shafts, H means the largest the shaft can be is the nominal size, and it can only be smaller.
Hey, Coach 啊，为什么那么多马来西亚人投资都亏钱？哦，因为他们不知道这里。
The H tolerance zone is important because it's taken as the middle. Shafts or pins with tolerance zones before H in the alphabet will never be the nominal size. Holes will always be larger and shafts will always be smaller. After H, there are a few tolerance zones, such as J and JS, where the shafts can be larger or smaller, but as you go further through the alphabet, the shafts will get larger and larger and the holes will get smaller and smaller. Holes always get an uppercase letter and shafts always get a lowercase letter. Okay, so now we have a naming scheme for tolerance zones. For a given fit, we will usually have one component driving the other one's required tolerance zone. In this example, where we bought the dowel pins, we have no input on their tolerance, so it was a shaft basis fit. If we're designing a shaft that has to fit in the purchased bushing, we can't control the tolerance of the bushing, so we have a hole basis fit. Shaft or hole basis fits often use an H tolerance zone, respectively, since the H tolerance zone contains the nominal size as one of the limits. If we're lucky enough to be designing both parts, we do have some discretion, but you would normally base your fit on whatever side of the fit is harder to change. The preference tends to be designing for a hole basis fit, as in general there tend to be more options for precisely reducing the diameter of a shaft than precisely expanding a hole. So what does a fit look like in the ISO system? It's simply the two tolerance zones specified next to each other. An H7G6 fit means, for example, the hole has an H7 tolerance and the shaft has a G6 tolerance. I've cut some holes in this piece of aluminum to show some examples of different fits. This is an undersized H6 tolerance dowel pin. The E7H6 and F7H6 are reasonably loose clearance holes. You can rattle the 12.7mm H6 dowels around a little bit, and they basically drop right through. The H7H6 and G7H6 are much closer fits, and could perhaps be used to locate parts while remaining removable. The JS7H6 is a transition fit that, as you can see, ended up being on the light interference side, but a rubber mallet would work to tap the pin in for a semi-permanent joint. Finally, the P7H7 is an interference fit and would probably require a hydraulic press, or at least a beefy arbor press to install. This might be a good time to point out that, contrary to my labels and my past example, individual holes and shafts can't be called JF7 or H7. The JS7 refers to the tolerance zone that the hole falls in. A hole that is 10.001 millimeters is in the JS7 tolerance zone, but it's also in the H6, H5, and JS5 tolerance zones. You have to remember that we can't measure the hole until after it's cut, and we have to specify the acceptable tolerance zone before it's cut. The fits also have some range to them. For example, these 3 holes are in the H7 tolerance zone, and these are 3 H6 dowels. Note how they fall through the holes at different speeds due to the minute differences in the clearance. The numbers themselves are actually determined by the IT system, the International Tolerance System. Every manufacturing process can be statistically analyzed and an IT number can be determined. This means that if I'm reaming a hole, I can look up the reaming process and see that at best I can achieve about an IT7. So I can't specify an H5 or a G5 hole if it's going to be reamed. Likewise, if you have to design something to fit inside a drilled hole, even if you don't have the tolerance for the hole in front of you, you can look up drilling and see that it has at best about IT10. So the whole basis for the fit is going to be around H10. So why would you use this system? Personally, I like how much information is available through just 2 digits. If I have to make a bearing seat on a shaft for an 8mm bearing, I can simply look up what tolerance is required from Machiner's Handbook or something similar. If I need a bearing seat for an 8mm bearing on a shaft that will see reasonably high loads, I can see that it recommends a JS5 fit. The machinists are not going to be happy about that. I know from the fact that it's JS, it'll probably be a transition fit and might need a little force to install, and the 5 tells me I'll need an IT5 process to make it, which will either involve very accurate turning or cylindrical grinding. As another example, if I want a nice sliding fit and the shaft I require will be in the H6 tolerance zone, I can simply specify a G7 on the hole tolerance without having to estimate how much allowance or clearance I want. Specifying a tolerance zone like this on a drawing does mean that the machinist might have to look up the actual numbers, so typically I include the fit as well as the tolerances. So knowing the different tolerance zones and having a list of a dozen or so preferred fits, we should be able to design parts that fit together how we want. We also have a means of vaguely checking if a manufacturing method will be capable of hitting those tolerances. In addition to the oft-used pin and hole example, the system can be used for internal-external parallel faces, such as keys and keyways, or other features of size. Well, that was a bit of a dry one, but hopefully you found it useful. If you find any mistakes, let me know in the comments so I can correct them. Thanks a lot for watching.
If you are struggling to lose weight and all the diets and exercise you've tried haven't helped, then you're going to want to see this. A shocking discovery just...
In this video, I want to talk about calculating a fit between 2 mating parts. And in this case, what we have is a hole through a part over here, and then we have a cylinder that we would like to fit into that hole. All right, so let me erase out those little marks that I just made right there. We can get started on this. Okay, so first thing we want to look at is the diameter of the hole. And put a dimension on here with the diameter of 1.00. This would represent the nominal size of that hole. And remember, the nominal size is the size that we can add or subtract a tolerance to. And then I'm going to put a tolerance of plus or minus 1/100th of an inch. Now, I want to point out something about this 1/100th. Sometimes someone, when they're talking about this, they'll sort of imagine there's another 0 on the end, and instead of calling this 1/100th, they'll call it 10,000ths of an inch. And when they do that, they're actually talking about the same thing. But just to keep the math simple, let's just keep this at 1/100th of an inch. All right, so what that means is that the diameter of this hole, which has a nominal size of 1, can vary as much as 1/100th of an inch in either direction. That is, it could get larger or smaller by 1/100th of an inch, and this part would still, or that feature would still pass inspection. So what that could mean for us is that at its greatest diameter, that hole could be as large as 1.01. That would be, we start with a nominal dimension of 1, and we add 1/100th of an inch, and we wind up at 1.01. Now, the other limit of size for this hole would be when we take the 1.00 nominal size and we subtract 1/100th of an inch, which results in the hole's diameter being smaller, and it'd be smaller by 1/100th of an inch, so it winds up being 0.99. Now, the diameter of 101 and the diameter of 0.99 represent the limits of size for this feature. So what that means is that the diameter of this hole needs to fall somewhere between a diameter of 1.01 and a diameter of 0.99. If it does that, it will pass inspection. Now, there's a way that we refer to these limits of size here, and we refer to one of them as the maximum material condition and the other one as the least material condition. When the hole is at its smallest, it's actually at maximum material condition, which I'm going to represent by just writing MMC. And when the hole is at its largest diameter, it's actually at least material condition. Now let's think about that for a second. When the hole is at 1.01, when it is at its largest diameter, we've actually removed more material from the part. That's why it's at least material condition. When the hole is at 0.99, there's more material remaining in the hole because the hole is smaller, and that's why we say it's at maximum material condition. All right, so let's try to design our cylinder to fit within that hole, and let's try to make sure that when that hole is at its smallest size, which is its maximum material condition, that this cylinder that we have over here will be 1/100 of an inch less than that. So really what we're going to try to calculate over here is what is the nominal size for this cylinder if we have a tolerance of plus or minus 0.01. Okay, well, the way we think about that all starts by coming over here and looking at our maximum material condition, because this is when the hole is going to be at its smallest. When the hole is at its smallest size, that's when we're going to have the most trouble making the cylinder here fit into the hole over here. When the hole is at least material condition, which would be at the 1.01, it's actually easier to fit that because the hole's larger. All right? So if we know that we're starting with the limit of size at maximum material condition of 0.99, then that tells us that the diameter of this cylinder, when it's at its largest, has to be 1/100 of an inch less than 0.99. So that tells us that the diameter that this cylinder can ever have and clear that hole, which is at 0.99, is when this cylinder has a diameter of 0.98. And since the cylinder would be the biggest when it's at 0.98, we would say at that point that the cylinder is at MMC. It's at maximum material condition. So since the cylinder can never be bigger than 0.98, what we need to do is come over here and look at our nominal size again, and we're going to actually subtract the 0.01 from 0.98, which leads us to a diameter of 0.97. And 0.97 is going to represent the nominal size of the diameter of the cylinder. So that means if this is nominal, then we could even subtract another 0.01 from that and wind up at the smallest diameter for this cylinder at a diameter of 0.96. And since the cylinder would be at its smallest diameter, we would say that the cylinder at that point is at least material condition. All right. So the answer to our problem of nominal size plus or minus 0.01 for this cylinder, we've pretty much calculated now. So I'm just going to write that in and then we'll just run through it real quick. So at nominal size.
Okay, I think this one will be more or less very much similar because all I want to bring up is the MMC and LMC's terminologies to get you the idea why least, okay, why maximum, and so on. So he explained that because of the maximum amount of material actually left on here. So this one is the minimum or the least material. okay, condition. So whereby you remove more materials, means that this workpiece basically have lesser material, all right, left on the products or anything.
Limits, fits and tolerances. What is this limit, fit and tolerance? And why they came into existence? To understand, let's take a scenario. Assume you become a manufacturer and a customer approaches to saying, I want to have a rod with exact 25 millimeters diameter. You being experienced manufacturer, you knew that regardless of how well designed or how carefully maintained, it's not possible to get exact 25.0000 millimeters. It is possible to get higher accuracy, with lots of effort and high-end technology, but never be able to get exact accurate dimension. There are two reasons for this. 1. Natural variation. And 2. Assignable causes. In natural variation, causes are inherent part of the process. They are random in nature that you cannot control. And assignable causes are identifiable, such as improperly adjusted machines, operator error, tool wear or defective raw materials. Therefore, you ask the customer to provide you with some limits between which your manufactured product should lie. So that if your manufactured part is little more or little less than 25 millimeters, the customer should not reject it. And customer, based on his requirement, will say, my rod should lie between limits of plus or minus some dimension. Let's take customer says plus or minus 0.2 millimeters. That means your manufactured shaft should lie between 24.8 millimeters to 25.2 millimeters. Means if you manufacture a rod of 24.85 millimeters, 24.95 millimeters, or 25.1 millimeters and so on, all shafts will be accepted, as long as your shafts are in between 24.8 millimeters and 25.2 millimeters. Therefore, limits is nothing but it is this plus or minus 0.2 millimeters. Here in this case, your basic size of the shaft is 25 millimeters. And plus 0.2 millimeters is your upper limit and minus 0.2 millimeters is your lower limit. If any of your manufactured shaft lies above or below this specified limits, that shaft will be rejected by the customer. This upper and lower limits are provided on both shaft and hole. Since we understood what is limits, after that comes tolerances. What is tolerance? Basically, tolerance is this region between upper limit and the lower limit. That is upper limit minus lower limit. In this case of shaft, it is 25.2 millimeters minus 24.8 millimeters, which is equal to 0.4 millimeters is your tolerance for the shaft. Similarly, the tolerance for the hole is also given, which is the maximum permissible size of the hole, that is upper limit of the hole, minus minimum permissible size of the hole, that is lower limit of the hole. Tolerance is further classified into 1. Unilateral tolerance. 2. Bilateral tolerance. 3. Compound tolerance. And 4. Geometric tolerance. In this video we will discuss above 3 types of tolerances. Unilateral tolerance. Suppose a tolerance on the shaft is given as 25 plus 0.05 to plus 0.1 millimeters. This means all the shafts should be more than 25.05 millimeters. And another example is 25 minus 0.02 to minus 0.1 millimeters, which means all the manufactured shafts should not cross 24.98 millimeters. We can see that the tolerance limits for both examples are lying on the either side of the basic size. For this type of tolerance we say unilateral tolerance. Bilateral tolerances. In this kind of tolerance, dimensions are specified in such a way that the tolerance region will lie on both the side of the basic size. We can see our first example. Shaft having 25 mm diameter with plus or minus 0.2 mm. In this case, the shaft can be of 25.2 mm or 24.8 mm. We can see that tolerance zone is lying above and below basic size. For this case, we say bilateral tolerance. Compound tolerance. When the tolerance is determined by established tolerances on more than one dimensions. For example, see in this figure, tolerance for the dimension R is determined by the combined effects of tolerance 40 mm dimension on 60-degree inclination and on 20 mm dimension. All three dimensions will determine the tolerance of R. This type of tolerances are called compound tolerances and should be avoided as far as possible. Since we understood tolerance and what are its types, now we will see what fits means exactly. Fit means how well the manufactured component will fit together when they are assembled. There are three types of fits: clearance fit, interference fit, and transition fit. Let's take the example of shaft and hole to understand all three. Consider a hole has a fixed diameter of 25 mm, and there are many shafts which are divided into three groups. Consider first group of shafts. Whichever shaft you take from this group and try to assemble in the hole, all the shafts enter easily in the hole. And we can notice there is a small gap between shafts and hole. In this case we say it clearance fit. Now second group of shafts. In this group whichever shaft you take and try to assemble, they don't enter the hole. Even if we want them to enter hole, we should apply external force. You see that the shaft is slightly bigger than the hole. In this case we say this group of shaft has interference fit. Now the third group. In this group when we try to assemble the shafts in hole, we notice that some shafts entering the hole and some are not. Which means some shafts are smaller than the hole and some are bigger. In this case we say this group of shafts has transition fit. Hope you understood what is limits, fits and tolerances. If you want me to make more videos like this, please support my work by subscribing, because that's what motivates me to make more videos, and click on the bell icon to receive all videos first. If you have any doubt or suggestion, comment in the comment box.
The stock market keeps going up, cryptocurrencies keep going up, NFTs keep going up, real estate keeps going up. It seems.
This is Dan Abbott. I'm making this short video to clarify how easily you can create or determine a class of fit on a shaft basis if you can start with a hole basis. And that's the easiest way to do this. People are making this harder than it is. No matter what, if you have a specific class of fit, that means you have a relationship between a shaft and a hole that is either a clearance, an interference, or overlaps. However you start, you have to have the same relationship between the shaft and the hole in order for it to be the same class of fit. Think of it as an equation. You can have an equation in math and say one side of the equation equals the other. Change either side, and as long as you change the other side in exactly the same way, it's still an equation. So the fits are going to be equal to each other as long as anything you do to every one of those numbers is the same. So we're looking for four numbers. And a reminder, I'm over here in 312 thou. That's what the letter C is. Shaft basis, and the category of fit was an LC6. That's what it was called out as. So I've got the LC6 section from the Machinery's Handbook. We're looking right down here in this row. These two numbers are going to be useful to us in terms of checking our work. What I'm looking at right now are those four numbers. It tells me that on a hole basis, the size of the hole at its maximum material condition is the nominal size, adding nothing, subtracting nothing. So if I look at the hole, the nominal size of the hole and the max material condition size of the hole are the same. So MMC for the hole is going to be 0.312, 312 thou. Right now, what does that mean? That means we're going to have another size for the hole, and the other size for the hole is going to be above, it's going to be right here, and that's going to be the least material condition. And that happens when the hole gets bigger. So the least material condition size for the hole is going to be 312 plus 1.4 thousandths of an inch, or 0.3134. Let's put a 0 right there. just to clarify that. So all I've done here is taken 1.4 thou and added it to this. So that gives me my hole sizes. Now I go over here to the other side, and now we're looking at the shaft sizes. Now here I'm going to go max material condition size of the shaft is going to be the nominal size minus a half a thou. So we're going to take the nominal size, whatever we start with. And in this case, the nominal size is 312. We're going to subtract a half of a thousandth of an inch from 312. So the MMC for the shaft is going to be 0.3115. That's 0.3120 minus 0.0005. That's going to give us this number right there, and that is the MMC for the shaft. Now we come down here, the least material condition size for the shaft is going to be the nominal size minus 1.4. Happens to be the same as this number, but that's kind of a coincidence. These others aren't the same. So we're going to subtract 1.4 from 3.12. That's going to give us 0.3106. So that's the least material condition size of the shaft. Now, no matter what, that's the same relationship we need to have for all of them. So if we look at max material condition size of the hole, max material condition size of the shaft, the difference between those two is 0.5 of a thousandth of an inch, which is represented right here as the minimum clearance. Look at the least material condition size of the hole and the least material condition size of the shaft, and the difference between those two is 2.8, which is the maximum clearance. Those numbers have to apply no matter what. So what are we going to do to change this to shaft basis? To change this to shaft basis, I'm just going to copy all these down. To change this to shaft basis, we need to make the shaft max material condition the nominal size. That's the only change we need to make to the shaft max material condition. We need to say that should be 0.3120. Now, what did I have to do to change that number into that number? I had to add 0.5 of a thou. Well, again, it's like an equation. If I add 0.5 of a thou to this number to get this one, I have to do exactly the same to the other three numbers. So now, what's 0.5 added to 0.3106? That's going to be 0.3111. What happens if I add 0.5 to this number? That's going to change it from 0.312 to 0.3125. And what's going to happen if I add 0.5 to this number? It's going to change that from 0.3134 to 0.3139. Now, the relationship among all those numbers is exactly the same. What's the difference between the maximum material condition size of the shaft and the hole? 0.5. 0.5 is right there. What's the difference between the least material condition size of the shaft and the least material condition size of the hole? 2.8. 2.8 thousandths of an inch. Same numbers we have right here. So again, it's like an equation. You can do anything you want to those numbers as long as you do the same thing to all four, and you'll have the same relationship between the shaft and the hole. Now we come over here to D, 312. So we're still dealing with 312 thou. So what I've done here, the one that refers to the category or to the range that includes 0.312 or 312 thou. So I'm going to do the same thing. I'm going to start by calculating on a hole basis, and it's easy. We just start by using max material condition size of the hole. It's going to be the nominal size. So we'll do the same thing we did over here. I'll say MMC for the hole is going to be 0.3120, 312 thou. Least material condition size for the hole is going to be 312 plus 1.4, or 0.3134 thousandths of an inch. That's on a hole basis now. And I'm just doing that by adding those numbers in. Now I come over here, and we have MMC for the shaft. MMC for the shaft is going to be nominal size minus 1.6. We subtract 1.6 from this, and we end up with 0.3116. 0.3104 is the difference between that number and 1.6. That's the max material condition size of the shaft. LMC of the shaft, the least material condition size, we have to subtract from the nominal size 2.5. We subtract 2.5 from this number right here, and we get 0.3095. So we're going to write 0.3095 over here. You know, that's on a whole basis, and most of you had no trouble with that because you're taking these numbers directly out of this table. Now, if we take a look at the relationship, the difference between that number and that number is 1.6. So the difference here is 1.6. That's the minimum clearance. The difference between these two numbers is 3.9. And again, that's 3.9 thousandths of an inch. So we have that to confirm that this is done correctly. So now all we have to do to get the, copy that, all we have to do to get this same class of fit for that size on a shaft basis instead of a hole basis is shift all the numbers in the same direction, the same amount, just like you would with an equation where you can add 5 to the left-hand side, and that means you just add 5 to the right. So in order to go from hole basic size to shaft basic size, I just need to turn the max material condition size of the shaft into the nominal size, the number I start with. Here, it was a hole. Well, I need that to be that number. So what do I have to do to get that number to be this number? I have to add 1.0016 to that. When I do that, I get 0.312, the nominal size of the hole in the shaft, but it takes adding 1.6 thou in order to do that. Well, if I'm going to do that here, I have to do it to the other three, or I don't have the same relationship. So what do I do if I add it down here? If I add it down here, I get 0.3111. That's what I get when I add 1.6 to this number right there. All right, that's fine, but I have to do the same thing over here. I have to add 1.6 over here. If I add 1.6 over here, I get 3136. Now that's the max material condition size of the hole. And if I'm going to do that, I then have to do the same thing down here. If I do the same thing down here, then I'm going to add 1.6 here, so I am going to get 0.3150. So now we take a look again to see what the relationship is. What's the difference between the max material condition size of the shaft and the max material condition size of the hole? 1.6, which is that number right there.